Solve minimum spanning tree problem by Prim, Kruskal, and reverse delete algorithms. Now we want to find the solution for this problem using solver. For the given connected graph, first we see how many vertices we have. From 0 to 8 we have all the numbers on the vertices. Then we have 9 vertices, and we are going to find n minus 1 edges to be in the minimum spanning tree. It means that if I consider xij as decision variable to decide whether we select the arc, for example, from 1 to 2 or not, if we select that to be in minimum spanning tree, then its value is 1, otherwise it is 0. And the total cost is going to be the sum for Cij's, Xij's. So what's the cost matrix? We will write all these values inside the square matrix. So first I write the name of the vertices here from 0 to 8 and copy and paste the transpose here and make it centered. To keep the Cij matrix or the cost matrix here in this selected part with all borders. And we keep two different highlighting. For the main diagonal, I keep the highlighting by yellow color, and I will explain why we highlight this. And for the other existing edges here, we are going to highlight some part of this matrix. Since if I want to select the edge connecting 1 to 2, it doesn't matter if I name it 1 connecting 1 to 2 or 2 to 1, you should select this only once. So to avoid selecting an arc twice, then we keep this Cij's only one part of this main diagonal, and I will keep in upper part, or I will keep an upper triangular matrix. It means that if I want to write, for example, this arc in the matrix, it is connecting 2 to 8 or 8 to 2, but I will read it 2 to 8, or it is x to 8 or c to 8. So in row number with index, not the index, with the name 2, and the column name 8, I'm going to write this intersection, that value 2. Now let's start from row 1. In the row 1, it means that from 0. From 0, we can connect to 1 and 7. From 0, we can go to 1 with cost 4, and we can go to 7 with cost 8. In the second row, from 1 we can go to 2. We don't consider from 1 to 0, because if I want to keep an arc or Cij, or I should be less than j. So from 1 to 2, not from 1 to 0. From 1 to 2 we have 8. And from 1 to 7 we have 11. 1 to 7, 11. Then we go to 2, and we start after the red or highlighted cell on the upper part of the main diagonal. From 2. From 2 we can go to 3 or 8. To 3 by cost 7 and to 8 by cost 2. And then from 3 again we start after the yellow cell. From 3 is here, we can go to 4 or 5 with the cost 9 or 14. 9 and the other one 14. 3 to 4, 3 to 5. From 4 we can go to 5 with the cost 10, and from 5 we can go to, we don't consider 4 and 3 because they're already inside the Cij matrix. We can go to only 6 with a cost 2. From 6, so here we have two possible cells to have a value inside them. From 6, we can go to 7 and 8. Both are possible. To 7 with cost 1, to 8 with cost 6. And from 7, we can go to 8. From 7 to 8. And this is also by cost 7. That's all. So we highlight the cells. So I select them all. And then highlight by another color, because later I'm going to keep this highlighted parts for decision variables and without any values inside. So I highlight this part with another color like this one. So these are the highlighted parts in CIJ. Now I want to copy and paste this matrix to keep the same formatting, but I will delete the values. So I copy this and paste it here. So this is my matrix V variables, but inside we have nothing, though originally they are all zeros. I can give zeros, but without zeros, or let me see if I can. Yes, I can give all zeros at once. So I can select them all and say equal 0, but this is an array, so I need to press and hold Control and Shift and press Enter. So originally I can say that they are all zeros. V transpose, so V transpose is going to keep similar format. I can copy, or maybe I can just let me check which one is good. If I start and write here, starting from here, equal transpose of this matrix. So this is going to be my V transpose. Now I can select all borders and this part. This is V transpose. I need identity matrix, which is going to be similar to this. So identity, we are going to have ones on the main diagonal. So for identity, I can keep the similar format, paste it here. But for identity, we don't need this formatting here. I can remove it. Don't fill, no fill. Now this is the identity matrix, but for identity, a main diagonal, we have all ones. And we cannot change because this zero has been created by an array formula. Then I need to delete them all. And write ones here and zeros everywhere. So this time I can write a 0 here, copy that one to row. When I finish, I can copy, well, like if I copy like this, then it will copy the formatting. I don't want to copy the formatting, so 0. Here we have 1, 0, 1. The rest are zeros again. main diagonal all ones. This is the identity matrix. We'll use this creating the upper bounds, and also in the conditions we will use this one as a lower bound. Identity itself as lower bound, and identity plus the adjacency as upper bound. So this is my identity matrix. Now we introduce another matrix. Here I call it M, which is the sum of V transpose, and identity. V originally is all zeros, V transpose for now zeros, but we want to decide the values for this highlighted cells. So at the final solution, we are going to have ones on the main diagonal here, based on the conditions that we will create, and some values ones on the other highlighted place, some of them, that creates a tree, and it's going to be exactly the minimum spanning tree. Now, the sum of these three matrices I can write here to M. I can write equal V plus V transpose plus identity. This will give us another matrix. We need to take this matrix to some power, and that power depends on the number of vertices. If it is n, we need to take this matrix to n minus 1. So since n is 9, I need to take this matrix to 8's power. And we will use mmult to multiply this m by itself to find m squared, another time m squared by m squared to get m to the 4. And if I need, for example, m to the 6, I can multiply m4 by m squared. If I need m5, I can multiply m4 by m. But since we need exactly m8, then I'm going to the next step, multiply m to the 4 by m to the 4 itself to get m to the 8. Now here I write another formula, which is mmult of two matrices. Which matrix? M and m square. M and m, which is going to be m square. I selected twice. So m and m squared gives us this. M times m gives us this m squared. Next iteration, I'm going to multiply m squared by m squared to get m to the 4. So here I write equal mmult m squared, which is this part, and again m squared. So this is m to the 4. And finally, m to the 8, which is going to be equal to mmult of m to the 4 and m to the 4. And we need the last matrix because we want to write a condition to make sure that the graph is connected, or the subgraph that you are finding by giving some values toCijs is a connected graph, or is a tree. Now, one of the conditions is going to be this one. When we find m to the m minus 1, we are going to find here minimum of equal minimum of these values based on the values for variables for xij's must be greater than or equal to 1. But since we are working with the integers, these matrices, this is going to be, or it means that the minimum must be different from 0. If the minimum is 0, it will show that the graph is disconnected. For the adjacency, I need similar format that I kept here. Then let's copy this matrix and bring here for adjacency. For the adjacency, we have ones for highlighted cells. Again, since it is all zeros, maybe it's better to bring the Cij since we don't have a array rule there. So I bring this one. Control C. So whenever you see that you are not able to do any modification based on the array rule, you need to delete everything. And so I brought this one since there is no array rule here. Instead of the Cij's, it's better to bring the Cij's and just change the Cij's to 1. This one shows that these vertices are connected, or there are some edges here. It means that if I want to select some edges, I'm going to select from the existing. The others means that there is no edge here if there is no 1 there. If there is no 1, the rest are zeros. If I don't write anything, they are zeros. So upper bound is going to be the sum of adjacency and identity. So here I write equal adjacency, this matrix, plus identity, that we have the identity here, plus identity. Now we have the upper bound. So adjacency, we just put the ones in the highlighted parts. And now we have ones on the main diagonal and also the highlighted parts. This is the upper bound. One more thing remains to continue with solver, and that is the objective function. What's the objective function? So we want to minimize the sum ofCij's, Xij's, or sum product ofCij's, which is this matrix, and Xij's, which is the variables here. This is our objective function. Now the objective is, this is sum product ofCij's, Xij's. Now I want to minimize this objective based on some constraint. Constraints are like this. All Xij's are going to be binary, 0 or 1. 1 means the edge is selected, 0 does not select. And Xij's are going to be less than or equal to this upper bound. It means that we cannot select those values that here there are zeros. Greater than or equal to identity, based on this ones here, means that we are going to select the Xi's or anything on the main diagonal. However, we don't consider them inside the tree, but based on the constraints, we need to select them all. So based on the zeros here in the upper bound and lower bound, it doesn't allow the Xij's to be, when Xij is less than or equal to 0, greater than or equal to 0, it must be equal, it has to be equal to 0. So we are not going to have any ones for those cells. But once we have a 1 here, some of them might be equal to 1, and to keep the graph connected without a cycle, we need the minimum for this m to the m minus 1 to be greater than or equal to 1. Now I select this cell that we have a formula there, and we use the solver. So we start from this cell as objective function. We want to minimize it. Changing variables are Xij's. We have Xij's here for variables. And we have some conditions. Conditions are all xij's, again we select the xij's, must be 0 or 1, they are binary. We add another one. Our xij's are less than or equal to the upper bound that we calculated or found the upper bound here, this matrix. And another condition, all the xij's are variables are greater than or equal to identity. It means that we want to select the or have ones on the yellow highlighted cells. So greater than or equal to identity is here. And last one, the cell that we calculated for minimum of m to the minus 1, this cell must be greater than or equal to 1. I can write 1 here, but or select that one that I wrote there. These are all conditions. 1, 2, 3, 4 set of conditions, variables, minimizing this cell. And this time we are not using the simplex. This is another method, which is evolutionary. It checks different possible matrices that can satisfy these conditions and selects the one with minimize the objective. And it will take a little bit of time, then we will see that once we run it, we need to wait for the solution from solver. If the graph is connected, for sure we will find the minimum spanning tree. Right now it shows that we solved almost 300 subproblems and still it checks the other trial solutions. Now we found the solution. It shows that the total cost for the minimum spanning tree is going to be 39, and the minimum spanning tree is going to be based on these variables. Let's see where we have these ones. Wherever we have 1, it means that these arcs are connected. 0 is connected to 1 and also to 7. 1 is not connected anywhere, but we know that it was connected to 0. From 1, we don't go anywhere else. From 2, we go to 3 and also to 8. From 3, we go to 4. From 4, we don't go to anywhere. From 5 to 6. From 6 to 7 and 8. This is the minimum spanning tree that we can find here. So the total cost is 39, and here you can see that in this matrix we don't have any zeros, so they are all integers. This greater than or equal to 1 means there is no 0 there. And once you finished, you should come here to this V and say which arcs are going to be inside the minimum spanning tree, or which arcs will create the minimum spanning tree. And as I mentioned, these are those arcs, so I select them one more time, only the ones, and highlight. However, I can write a condition. If the value is 1, then change it to other format. But for now, I just change the color for this to show that these cells shows the minimum spanning tree for this problem.